This is going to be our second lecture, and in this for AMAT 112, this is calculus, and in this section, in this lecture, we're going to go over 1.2, some mathematical models, and it's basically just going to be a broad overview of all the most important functions um, that are used in applications, and so they're important applications, and they have theoretical importance also. They're used throughout mathematics as well. So let me share my screen. Let's see. I'm gonna actually work through the book. I'm using a different PDF viewer so I should be able to draw on it more easily. Yeah, there we go. All right. So yeah, so I'm not going to go through the applications a whole lot in this course. Um, it's hard to overstate the importance of mathematics and how useful it is in describing the sciences and describing phenomenon in the physical world. So if you're interested, you can read this little description on trying to like glorify mathematics in a sense. I'm not going to go through all of that. Let's just get right into the mathematics, especially because this is summer course and we're limited on time. So the first type of function we're going to look at, and is probably the most important type of function, is a polynomial function. So polynomial function. And a polynomial function is going to be a function of the following form. So you have an, so you have these an times x to the n, and then an minus 1 times x to the n minus 1. And then you have some intermediate terms, and then you have a2, x2, a1, x, and then a0. And n is going to be some non-negative integer. So n is in the set n, and this set consists of the numbers 1. Actually, well, okay. Yeah, I guess 1, 2, 3, 4, etc., all the way to infinity. Some people include 0, and 0 actually is an important case. So n is these are going to, n is the leading exponent of the leading coefficient. That's a non-negative number. And then a0, a1, a2, and an are constants. These are the coefficients in the polynomial. And it's clear that the domain of any polynomial is just all real numbers. There are no restrictions um, to the sorts of numbers that you can plug in. So, and then we have that an is called the leading coefficient. We always assume it's just non-zero. Otherwise, if this term right here is 0, then this will be the leading term, and you just keep going down the line until you get your first non-zero coefficient. Whatever is the first non-zero coefficient, with the largest subscript right here, that's going to be your leading coefficient. And um, if an is non-zero, then this is the degree of the polynomial. N is the degree of the polynomial. So here's a 6th degree polynomial. This is a 6th degree polynomial. And we have some other important ones. So let's write these down. So we have when n is 1, we have p of x is equal to a1x plus a0. And this is a linear polynomial. The graph is just a line. It's a line with slope a1 and y-intercept 0, comma a is 0. So it's a linear polynomial. When n is equal to 2, we get that, I think we're using p, yeah. P of x is equal to a2x2 plus a1x1. Sorry, no, not a sub 1. Just x to the first power. But that doesn't even matter. You don't can just ignore that. So It's a2x2 a1x plus a0, and this is a quadratic polynomial. And the graph looks like something like this. I mean, really the only graph you need to memorize is the graph of p of x is equal to x squared. And if you graph that, it's going to look something like that. It's going to start at zero and open up like a parabola. That's pretty terrible though. Let me try doing a little bit better though. So and the reason why you only need to remember this case right here, that just the x squared case, is because any other quadratic polynomial is just going to be some transformation of this basic polynomial right here. So you could have, and you can see that as a transformation by completing the square. So if you complete the square and you want to, so if I, for example, if I give you, let's say I give you, well, let's say I just take this one right here, x squared plus x plus 1. Let's complete the square on that. Let's say this is x squared plus x plus 1. To complete the square, you take half of this coefficient right here and square it. So you get x squared plus x plus 1/2 squared plus 1. But since you added in 1/2 squared, you got to subtract 1/2 squared. And then you can complete this, you can factor this right here. So you get x plus 1/2 squared. And then this will be 1/4, so plus 3/4. And so what this says is that you just basically take the x squared function and the one you shift, so shift left half a unit. That's what this 1/2 here indicates. And then shift, we have plus 3/4 up 3/4 of a unit. So in other words, this point right here, the x squared function started at this point and it moved over half a unit and then up 3/4 of a unit to here, and then it opens up. So as long as you know the graph of x squared, you can get the graph of any other quadratic polynomial by completing the square. So this is a polynomial in general, and really the only cases we're going to look at are linear polynomials, quadratic polynomials, and then sometimes even put up here the n equals 3 case, cubic polynomials. So in this case, p of x is equal to a3 x3 plus a2 x2 plus a1 x plus a0. This is a cubic, oops, polynomial. Whoops. And again, the special case that you need to memorize is this. That's all you need to memorize. And the graph of that, oops, let's draw the graph of that. It looks something like this. And then any other cubic polynomial, as complicated as you can imagine, is just going to be some transformation of this. Maybe a shift to the right a unit and down 1 unit, or maybe you stretch it vertically or horizontally or something like that. Now determining exactly how a given cubic polynomial is a transformation of this like elementary cubic polynomial is a little trickier than the quadratic case. In the quadratic case, you just have to do this completing the square trick, but it's not, you don't always have such a trick in the cubic polynomial case, but you can work it out in some cases. Sometimes you have to do some clever factorization or whatnot. All right, so that's the polynomial, and then as I said, here's a degree 1 polynomial is of this form, so it's a linear function. a degree 2 polynomial is of this form. We already saw this. This is a quadratic function. And as it says here, the graph of the quadratic function is always a parabola obtained by shifting this parabola. And then the parabola opens up if A is positive, and it opens downward if A is negative. Because this coefficient right here determines, well, when you have this negative here, let's just even think about this A right here. Remember, when you multiply by a negative number, it reflects it over the x-axis. That's what that transformation does. And if some of that doesn't make sense to you, that's something you'll learn in pre-calc. But if you don't remember how those transformations work out, just feel free to email me and we can maybe meet somehow to have a Zoom meeting and we can go over those. So here's a polynomial of degree 3. We saw that already. It has that kind of form. So here are some cubic functions, and they can get complicated, but again, you can always kind of figure out for most of the functions we're going to deal with are basic transformations of the simple ones. All right, so this is not an interesting example. I'm going to move on. Oh, here are the power functions. This is when you have we actually already looked at these cases right here. We saw this one, and this one. And then you have x to the fourth. You can see it almost basically looks like a parabola, not much different. And then you x to the fifth. Basically what happens when you have x to an even number, you have this parabola looking shape. But as the even number gets larger, you can see it flattens out near the origin. And then you have the odd case, x cubed, x to the fifth. They all look the same. X to the seventh looks roughly the same. But you can see near 0, it flattens out more because when you take a number between 0 and 1 and you say raise it to the fifth power, it becomes even smaller. When you take a number between 0 and 1 and raise it to the seventh power, it becomes even smaller. So that's why it gets flattens out near the origin like that. It's those numbers getting closer to 0. Yeah, so here's just a summarization of what I said. So the graph of this right here, the graph of this depends, this graph depends on whether n is even or odd. If it's even, then the graph is similar to a parabola. If it's odd, then it's similar to the cubic function y equals x cubed. Yeah, and then it says, however, as n increases, the graph of y to x n becomes flatter near 0, and it becomes steeper when you go far away from 0. So in other words, if x is small, then x squared is small, x cubed is even smaller, x fourth to the fourth is even smaller. So it's flattening out near the origin. So just the observation I made, but put in words. Okay, so here's the even case. So you have x squared. It's a comparison of these points, and notice they all intersect here. 1, 1 and 1, -1, 1 are points on x squared, x to the sixth, x to the fourth. And they all basically have that same shape, as I said, but it flattens out more. And then once you get, so here's here's 1, here's -1. And when you look at x that satisfy this, that is x away from 0, so like over here and over here, you can see the graph becomes much steeper. See the red curve and the green curve, it's becoming much steeper. It goes up to infinity faster, you would say. And then here's the odd case. They don't do x to the 7, but that's right, I guess. They all have the basic shape, same shape. So that's the polynomial functions, and these are power functions, but really they're just a special case of the polynomial. Here's where we get something different now, and that's the root function. This is something that's completely distinct from polynomial. So the root function is a function of this form right here. F of x is equal to x to the 1 over n. So far notice that the function we looked at, the domain is all the real numbers. But now root functions can have different domains. It depends upon the n itself. Is it an even number or is it an odd number? So here's a special case, n is equal to 2, that gives us the square root function. And we know square root function can only take in non-negative numbers. Remember, when you have a function, say you're given just the rule of the function, domain. Remember, domain means the largest set of numbers for which the function makes sense or is well defined, and this is the largest set of numbers. You can of course think of the square root function on a smaller domain. Say you can consider it on 1 to infinity, or maybe like 100 to infinity. There's the square root function is defined on these intervals also. And for certain, maybe for certain applications, that's the domain you want to take, but usually the convention is that the domain is the largest set. All right, so now when you have when you have let's say y is equal to the square root of x with x positive, if you square both sides, you get y squared is equal to x. And so you can see that the graph of this is really the graph of that, and it's a sideways parabola. I would say it's actually the upper half of the parabola, x equals y squared. So that's this graph right here. This is our square root function. There's of course this other branch, but we're considering x positive. So because x is positive, that implies that y is also positive, right? When you take, well, actually no, it's not because x is positive. It's just because so square root of x is always positive, so that implies that y is always positive. So you just ignore this branch right here. Now, as I said though, technically, the graph of this is that whole parabola. But because we have this restriction on y, we only graph the top half. So now, and we get the same sort of dichotomy we do with the power function. So when the values of this exponent are even, this function basically looks like x square root of x. Just like with x squared, x to the 4th, x to the 6th, they all look the same basically. When n is equal to 3, we have this function right here. And now note, you can take the cube root. This right here is defined for positive and negative values. And x equals 0, of course. You can plug in 0. So that's why when you take this cube root of x, it's defined on the positive x-axis and the negative x-axis. So for example, the cube root of -8 is going to be -2. That's because when you take -2 and raise it to the third power, you get -8. That's how this root function is defined. It's defined as in terms of this. This is basically inverse functions. Um, all right, so and again, the graph of this thing is similar to that of the cube root when n is odd. So you get the same dichotomy. You get the same dichotomy as you do up here with the power functions. So the even case looks basically the same, and the odd case basically looks the same. It just flattens out near the origin. All right, so the next kind of function again is not like the other ones we've seen, and this is a reciprocal function. This is when you take it's kind of like a power function, but with n equal to -1, but it's distinct from the power functions. So this is going to be the function x to the -1. And this looks like it looks like this graph right here. This is the graph of x, y is equal to 1 over x. So yeah, this is an important one to remember. And then you have, I guess, the -2 when the exponent is -2. Uh, yeah, as I'm not gonna like go through all this. Like it says there's yeah, so it says this function arises. So x to the -1 arises in physics and chemistry in connection with Boyle's law, which states that the temperature is constant, the volume V of gas is inversely proportional to the pressure. So there's an application if you're interested, but I'm not really interested in that for our purposes, just to save time. And then again, there's another, well, yeah, this is the inverse square law about illumination of an object by a light source. You can read that if you want. But for us, um, this is what y equals to 1 over x squared looks like. So this is another important one to remember. All right, so the next kind of function we want to look at is rational function. These are again um, the rational function. Let me say this: so a rational function is a function of this form. It's a ratio of two polynomials. So you have a numerator denominator of polynomials, and it's clear that every polynomial is a rational function. You just take q of x to be the like trivial polynomial, just always one. And in that case, this fraction just reduces to p of x. So every polynomial is a rational function, but actually not the converse. And the domain in this case consists of all the values of x such that the denominator is non-zero. So it's going to be like this. And because we're talking about polynomials, there are only um, finitely many x, finite meaning not infinite, only finitely many real numbers such that st just means such that q of x is equal to 0. So you're to get the domain of this rational function right here, you take the real line and you just chop it off at these points where q of x is equal to 0. So for example, they have this example right here. You have x, the denominator is 0 when this is 0, and it's clear that this implies x is plus or minus 2. So the domain of this is going to be all the x that is not plus or minus 2. And in interval notation, that's going to be -infinity to -2, union -2 to 2, union 2 to infinity. So you just take the real line and you chop off, you like remove or extract the roots of the denominator here. And as I said, they're only going to be finitely many. So you're only going to have to do like a finite union like this. And the number of intervals you have to union together is equal to the number of roots of your polynomial. All right, so that's that. Eventually we're gonna look at how to analyze we're gonna look at how to analyze such functions and graph such functions. And you can see that this graph right here is actually even. It has even symmetry. So this function right here, you can see that it's not hard to check algebraically too. That you have this property holds. So if you replace x by negative x, x negative x to the fourth would just be x to the fourth, negative x squared would just be x squared, and then this negative x squared would just be x squared. So it clearly satisfies this property, and you can see that it has that even symmetry reflected in the graph. All right, so the next kind of function we look at are algebraic functions, and this is just basically everything. This is these are all the possible functions that it can be constructed using operations such as addition, subtraction, multiplication, division, and roots. And so you basically start with polynomials and you just combine them in all possible ways. So here's an example, here's another, and then here's another example. So they can get pretty awful, you can see. So it's just like just a bunch of different ways of combining these operations in this described in this sentence right here. So here's an example with, I guess this comes from relativity. Yeah. Yeah. So yeah, the applications of mathematics are endless. And if you care about your technology, the fact that you can use computers and cell phones, etc., you should care about mathematics because none of this would be possible without mathematics. The modern world would not be possible without mathematics and the discovery of mathematicians and inventions. All right, so that's algebraic functions. Not a whole lot to say there. They can be pretty. This is like the Wild West right here. In other words, the algebraic functions represents the Wild West of all functions. Another type of function we can look at are trig functions, and these are very different. I'm not going to fully recall the definition, but you can see that they're reviewed in on reference page 2 and in the appendix. Remember, there's two ways you can define trig functions. You can define them using right triangles, or you can define them using the unit circle approach. And I prefer the unit circle approach. And let me just recall that one at least, actually. That one is to me, a lot easier. So basically, the idea is this, to define the trig functions. The idea is to reimagine the unit circle. So remember, unit circle is described by the equation x squared plus y squared is equal to 1. So xy is a point x comma y is on the unit circle if and only if it satisfies this equation here. So on the one hand, the unit circle is a two-dimensional object, right? You need two parameters, x comma y, to describe a point on the circle. But actually, the unit circle can also be thought of as a one-dimensional object in the following way. So you pick a point. So it's certainly true that the real line is a one-dimensional object, right? So I take 0 as my reference point, and I can like measure distances relative to 0. So maybe I'm here or over here. And the reason why the real line is one-dimensional is because I only need one parameter to describe position on the real line. So I give you a number, it's either positive or negative. If it's negative, it means you move to the left of 0 a certain number of units, and if the number is positive, it means you move to the right of 0 a certain number of units. And we use this point 0 as like this origin, it's our fixed point. Well, you can do the same thing with the circle. You take this fixed point here, 1 comma 0, and if you imagine that you're living on the unit circle, that is, your universe is the unit circle, you're an ant on the circle, there's only two ways you can move. You can move counterclockwise or you can move clockwise. But that means you only need one parameter, right? So living life on a unit circle only requires one parameter to describe position. Oops, I don't know if I'm spelling this right. No. You only require one parameter and you call it t. So you have this number t, and t is going to the t will give you a unique position um, in the space. So basically, I give you a t value. You start here. If the t is positive, that means you move counterclockwise, and then maybe you say you land here. If t is negative, that means you move clockwise, and maybe you land here. And when you wherever you land on the circle, it's going to determine a points x comma y. Okay, so there's this like dictionary or this way of transcribing between viewing the circle as a two-dimensional object using this equation, or as a one-dimensional object using this single parameter. So given a parameter t, you travel along this circle a certain amount, and you either clockwise or counterclockwise, and you land here, say at x comma y, and it determines a point in the plane. And then the trig functions are just simply the x and y coordinates. So sine of t. So say you move, let's say, so say you move t, and it means you move along this arc right here. It means you move along this arc. So this distance to travel was t, and let's just say it was positive. Okay, for simplicity. Then sine of t is just the y coordinate. Oops. Cosine of t is just the x coordinate, and then tangent of t is the y over the x. So pretty simple. Once you realize that the unit circle described this by this equation is really just a one-dimensional object, and if you are living on the unit circle, you only need this one single parameter to describe position. And then you just define the trig functions as follows. So if you didn't completely follow that, I encourage you to read this reference page in the appendix or meet with me if necessary. So we're, as it says, we're always using radian measure. So this isn't like an arc length. T is arc length. It's like an arc length, but it's also an angle. It also can be interpreted as an angle. It's like how much do you have to rotate through to get to that point on the circle. You can imagine like you have this point where it like this is like a bracelet. In other words, the unit circle is a bracelet, and you have this point here, and you can like slide it along the bracelet, a value of t, and that is equivalent to either moving through an arc length or rotating through that t value. So these are just there's like this duality. There's a lot going on. The unit circle, there's a lot of information packed in the unit circle. So remember the equation of the unit circle, remember this way of translating between the unit circle two-dimensional approach and the one-dimensional approach. All right, so here are the graphs of sine and cosine. You can see that they're periodic, and that basically comes down to the fact that if I travel a distance of t, and then I travel a distance of 2 pi or 360 degrees, you're going to land back at the same spot. So t and t plus 2 pi determine the same spot on the circle. The state you'll end up at the same position. So that's why these functions are periodic. And they're always bound between, so if you can see the domain is of these two functions is any number. You're allowed to plug in any number. You can travel around the circle. You'll kind of loop around the circle infinitely many times, but you can do that as many times as you want. So the domain of these functions is negative infinity to infinity. But because you're talking about points on the unit circle, the range is going to be between -1 and 1. So sine is a function from r to -1, comma 1. And why is that? Well, sine of t is your y coordinate, right? Um, so now we have x squared plus y squared is equal to 1, right? So y squared is less than x squared plus y squared equal to 1, right? So remember, if you're on the unit circle, you satisfy this equation right here. But certainly y squared is less than x squared plus y squared, right? Because these are two positive numbers. If you start with x squared and you add another positive number, you're just going to make it bigger. So that's why y squared is less than x squared plus y squared. But you know x squared plus y squared is equal to 1. So that implies that y squared is equal to 1. Or sorry, less than or equal to 1. And if you take the square root of both sides, you get that y is less than or equal. The absolute value of y is less than or equal to 1. But y is just sine t. So you're saying sine of t is less than or equal to 1, which is the same thing as saying that sine of t is between -1 and 1, which is exactly this inequality right here. And you could do the same sort of argument for cosine. Instead, you would just say x squared is less than or equal to x squared plus y squared, which is equal to 1. And then you get x squared is less than or equal to 1. So you get an equality like this, and then you take a square root like you did here to get the absolute value of x is less than or equal to 1. And then from there, basically this inequality follows. So, and they write it in absolute value form also right here. So here's a proof. This right here is proof that this inequality holds. I will occasionally write proofs. So just a warning. So you're gonna have to, but you shouldn't be scared by proofs at all. So if this, yeah, so here's the proof. The claim is basically that this is the claim right here. Absolute value of sine x is between 1, is less than or equal to 1. And the proof is, this is the proof as follows. You'd basically take a t value, it's going to determine a point x comma y on the unit circle. So x comma y has to satisfy this equation. And then you just go through these steps that we did here. And that proves that. And then another property, which I already alluded to, is that sine and cosine are periodic functions, and they have a period of 2 pi. So this is for all, these two equations hold for all x in R. So, and that because if you, like I said, if you, so let me just see. If you rotate or travel t, say t lands you, has you land there, and then you travel around 2 pi, you're going to land at the same spot. You just did a 360. So you go, so this point right here corresponds to t, and it, or sorry, I should say t and t plus 2 pi correspond to the same point. And by the same argument, t plus 4 pi, t plus 6 pi, t plus 8 pi, they all determine the same point on the circle. So that's why you have this periodic condition here. Because, and remember, I know that they're in this book they're using x. Well, x is just a dummy variable. You can replace these equations by t. You can say sine of t plus 2 pi is equal to sine of t, and you can write cosine of t plus 2 pi is equal to cosine of t, and the argument still holds. And you remember, cosine gives you the x coordinate, sine gives you the x coordinate. So if t and t plus 2 pi and t plus 4 pi all determine the same point, then they're all going to have the same x coordinate, and they're all going to have the same y coordinate. So that's why this equation holds. All right, so here's an example. Find the domain. So this would be, well, I guess, this is technically not, what's the terminology? I want to make sure I'm using this right. Algebraic function. All right, this is not technically an algebraic function because you start with polynomials, but yeah, I guess it's just a function that doesn't fit in any category. So you want to find where is this function defined? Well, the problem, again, remember, domain is largest set of values for which the function makes sense or is well defined. So the only place that you could have troubles is where the denominator is zero. So just take this denominator right here and set it equal to zero. So and when you do that, you can solve for cosine x, you get that. And now this is just a fact that cosine x is 1/2 if and only if x is of this form right here. And this is for any integer n. So n is just any integer, and the integers are denoted as follows. Let's use this word z, or letter z, and it consists of -3, -2, -1, 0, 1, 2, 3. And the dots just mean you go off to negative infinity, and these dots right here mean you go off to positive infinity. So I might use this notation, so keep track of that. And to figure this out, it's not that hard. You know that it's certainly true that cosine of, if you just draw the unit circle and you remember it, that cosine of pi over 3 is the same thing as 1/2. But then if you take cosine of pi over 3 and you travel 2 pi n times, you're going to land at the same spot, so your x coordinate is going to be 1/2 also. So all these points, all of these numbers here determine the same position on the unit circle. All right, so now let's see. So we have the tangent function. I defined that already. I defined it as the y coordinate over the x coordinate, but this is the same thing. You can see, right? Because remember, the sine gives you the y coordinate, the cosine gives you the x coordinate. So it's the same definition. Here's the graph right here. And we have that it's not defined on the whole real line. So there's going to be points where it's not defined, and these are the points right here: -pi/2, -3 pi/2, pi/2, 3 pi/2. We're actually going to have what are called asymptotes here. We'll talk about those later, but they're just basically vertical line. These are vertical asymptotes. They're going to be horizontal asymptotes also. These are just vertical lines where the graph gets very, very close to the line, but it gets arbitrarily close. Maybe it touches through it, but in this case, it doesn't. It could go through it, but it doesn't necessarily go through it. In this case, the graph of the function does not go through its vertical asymptotes. So why do we have vertical asymptotes at these values right here? Why is it not defined? Well, it's because this is where cosine is 0. So cosine is 0. Again, if you just consult your unit circle, you know it's cosine is zero at these values right here. So I guess more generally, it would just be pi over 2 plus 2 pi, or no, just pi n, I guess. Or n, in any integer n. Yeah, so if n is 0, you get pi over 2. If n is -1, you get -pi/2. If n is 1, let me just write a couple out. So if n is 0, then you're talking about x is equal to pi over 2. If n is -1, you're going to get x is equal to pi over 2 minus pi, which is equal to -pi over 2. When n is 1, that implies x is equal to pi over 2 plus pi, which will give you 3 pi over 2. So this formula right here does describe all these numbers in this list. And the numbers in this list are precisely where the cosine is 0. And that's precisely where the tangent function is not defined. That's why we have these vertical asymptotes here. All right, so the next kind of function we'll want to look at are so-called exponential functions, and related to that are going to be the logarithmic functions. These are actually inverses of each other. We should be talking about inverse functions at some point. Let me see. I guess. Oh yeah. So we're going to look at these functions again in section 1.4 and 1.5. It turns out that these functions are inverses of each other. I guess I don't really like the way that they're introducing these. We shouldn't even talk about these right now at all. Yeah, so I'm just gonna skip them actually. Um, there's no point in going over them because they're not, the book is not even properly introducing them here. So just ignore those for now. So we have an example six. This is kind of dumb. Skip that. All right, so here are just a summary of the functions we looked at and their graphs. And that's it. So here, I'll just give you a second to look at this. So we got our linear functions. Again, these are polynomials where of degree one. So polynomials of degree, actually, I should say zero or one. This would be the 0 degree case. This would be the 1 degree case, the first degree case. And then we have power functions. Again, these are just polynomials, but they're like the elementary polynomials, the very basic ones. We saw these ones. There's the root functions. Here's some reciprocal functions. We saw these a little bit. So we have 1 over x. And then you can see there's again this dichotomy when you have x to the 1, x to the third, they look the same. So when you have 1 over x to an even power or odd power, they're all going to basically look the same. They kind of flatten out, you can see, as x goes out to infinity. And that's because when you compare x and x cubed, when you cube a large number, it gets even larger. And then when you take 1 over a large number, it's small. So that's why the x cubed flattens out faster than the 1 over x. And when you have x squared, x to the fourth, they basically again look the same. And so you have this dichotomy of even and odd. And you can see that this one, that the x to the fourth flattens out faster than x squared. And again, because when you take a number, you square it. Let's say you take a large number and you square it, you get a large number. But if you take that same number and you raise it to the fourth power, you get even larger. Now take the reciprocal. When you take the reciprocal, you of a large number, it becomes small. So that's why this x to the fourth flattens out faster. Here the graph of the log and the exponential. We're going to see those later. And then here the graph of the trig. And that's all we have for today. I think I'm going to package it lecture one and two. Like they should be watched on the same day, I guess. I don't know. Still working out. I'm actually, it's, well, you can see I'm recording these well in advance. So I just want to make sure I have all these videos ready for you. But I don't know exactly how I'm going to like distribute these videos. Maybe I'll upload them all at once or, one or two a day. I'm not sure. All right, that's all we have for now. So